Okay, Lecture 19 is going to coordinate with this week's homework, which is titled Lecture 13 or 19, Gases Part 2. Some of this stuff we've already gone over, but some of you guys still need this. Dalton's law of partial pressures. For a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. Jonathan Dalton. That's P1 plus P2 equals P total. So if I have 100.8 grams of oxygen, 289.8 grams of nitrogen pumped into a 6-liter scuba tank at 20 degrees Celsius, find the partial pressure of each gas, then find the total pressure. Well, I can just use this right here, convert grams to moles, then I'll have N, then I'll have V, then I'll have T, solve for pressure. I could do that for each one. Or I could solve for moles of this and solve for moles of this and add them together and plug it in. So grams to moles for nitrogen, plug it into PervNert, get 41.5 ATMs. Grams to moles for oxygen, plug it into PervNert, get 12.6 ATMs. Add them together, the total pressure is 54.1 ATMs. Okay, now I want to show you how they do it with an ice chart. A sample of nitrosyl chloride is placed in a sealed container. When equilibrium is established, the pressure of nitrogen monoxide is 0.458. Find the pressure of chlorine. Well, if I start with 0 and 0, because these are the products, this side has to gain 2x, this side has to gain just 1x. If I already know this value right here, 0.458, because I was told that, then this guy has to be half of that, which is 0.229. Mole fraction is the percent composition by moles of a single component in a mixture, represented in its decimal form. Basically, it's just the percentage of moles that are in the mixture, but it's not a percentage, it's in the form of a decimal. So find the mole fraction of each component. Well, all you're going to do is this. You're going to add up all your moles. Then you're going to take this guy, divide it by the total, and that's going to be its mole fraction, 0.620, which is, 62%. For argon, it's going to be 2.5 divided by the total, or 0.231, 23.1%, and 1.60 moles for chlorine divided by the total, 0.148. Obviously, these guys right here should add up to 1. A gaseous solution contains neon, hydrogen, and helium. The mole fractions of neon and hydrogen are known to be 0.233 and 0.478. What is the mole fraction of helium? We'll just add these two together and subtract them from 1, and the answer would be 0.289. Okay. You can find the partial pressure of any component in a gas mixture just by multiplying the total pressure by its mole fraction. For example, if the mole fraction of oxygen in a container is 0.97, if the mole fraction of oxygen in a container at 0.97 atm is found to be 0.21, what is the partial pressure of oxygen? Well, isn't this telling me that this container is 21% oxygen? Well then, my total pressure, 21% of it, comes from oxygen. So I'm going to simply take the 0.97 times my percentage, or my mole fraction, and get 0.20. So out of the 0.97 pressure, 0.20 of it comes from oxygen. The following reaction goes to completion. In a 6.3 liter vessel at 78 degrees Celsius, the vessel contained 2.5 moles of hydrogen and 1 mole of chlorine. Okay, we're going to find the mole fraction of all the gases, find the total pressure, and find the partial pressure of hydrogen. First of all, I'm going to plug in my original amounts, 2.5 moles of this and 1 mole of this right here. Notice for every 1 mole of chlorine, don't I need 1 mole of hydrogen? Do I have 1 mole of hydrogen? Yes, I have more than 1 mole of hydrogen. So this is going to be my excessive reactant. This is going to be my limited reactant. So I'm going to lose all of this, lose 1 of that, gain 2 moles of that. This is going to end up being 0. This is going to end up being 1.5 moles, and this is going to be 2 moles of HCl. So at the very end of this reaction, I'm going to have 2 moles of HCl, 1.5 moles of hydrogen, and 0 moles of chlorine. So find the mole fractions of everything at the very end. Hydrogen is going to be 0.429 or 42.9%. Oxygen is going to be 0.571. Find the total pressure in the vessel after the reaction. Well, I can plug my moles, both my moles, in for Pervnert and get 16. Now, if I wanted to find the pressure of hydrogen after the vessel, in the vessel after the reaction, I could just plug in my moles of hydrogen into Pervnert and solve, or I could take the total pressure, which was 16, and multiply it by its mole fraction, 0.429, 6.9 ATMs. Just another reminder, because some of you guys struggle with this, every time you collect a gas through water, it's called a wet gas. Okay? And what do you have to do with that wet gas? You have to subtract the water vapor pressure. When measuring the volume of a gas collected, one must first line up the water levels inside and outside of the graduated cylinder. This ensures that the pressure inside the cylinder is equal to the atmospheric pressure outside. So in a reaction that produces oxygen gas, 37.45 milliliters of gas was collected over water at 25 degrees Celsius at 1.01 ATMs. The vapor pressure of water at 25 degrees Celsius is 23.76 millimeters of mercury. How many moles of oxygen were collected? Well, the first thing I'm going to do is I'm going to switch this from millimeters of mercury to ATMs. Then I'm going to take my pressure and I'm going to subtract the water vapor pressure, 0.98. Now I can plug this into Pervnert right here. 0.98 is my pressure. The volume, I believe, was 0.03745. I think they gave it to us in milliliters. We just shifted that over to liters. 0.0821, temperature is 298. I solve for number of moles, and I get 1.5 times 10 to the negative third. Just don't forget, when it's wet gas, subtract the water vapor pressure. Okay, the average kinetic energy per mole of gas is always equal to 3/2 RT. However, since we're talking about energy, kinetic energy, we're going to use a different R value. We're going to use the 8.314 joules per mole Kelvin R value, because energy is measured in joules. So what is the average kinetic energy per mole of molecules at standard temperature and pressure? 3/2. This is going to be 8.314. Standard temperature is 0, which is 273 Kelvin. So 3,400 joules per mole, or 3.4 kilojoules per mole. What is the kinetic energy per gas particle? Well, that's going to be 1/2 mv squared. Okay, but remember, the larger the mass, the lower the velocity. Velocity is going to be measured in meters per second, and the mass of the particle will be in kilograms. And once again, remember, the larger the mass, the slower the speed. Here's molecular speed right here. Hydrogen has a larger speed than oxygen. Okay, if you wanted to measure the average speed that these molecules are moving, it's called the root mean square velocity. It's the average velocity of a specific type of gas molecule at this specific temperature. It equals the square root of 3RT, kind of like the kinetic energy equation, divided by its molar mass, because it is molar mass specific. R, once again, is going to be 8.314 joules. Now, a joule, if I break down a joule, it's equal to kilograms meters squared per second squared, which means that my molar mass needs to be in kilograms. So the average velocity of a diatomic gas molecule is found to be 515 meters per second at 25 degrees Celsius. What is the molar mass of the molecule? Identify the molecule. Okay, so I'm going to use this right here. I have my root mean square. It's 515. I've got 3. I've got 8.314, and I think they gave me the temperature, 25 degrees Celsius. Okay, we're going to be solving for molar mass. So the first thing I would personally do when I plug in all my numbers is I would probably square both sides. Okay, that's going to get rid of this thing right here. And once I do that, if I rearrange this equation and solve for molar mass is going to equal 3RT divided by the root mean square squared. So 3, R is 8.314, temperature is 298 divided by the 515, and then we have to square it. And we get an answer for molar mass of 0.028, but remember that's going to be in kilograms. So what is that in grams? 28 grams per mole. And what diatomic element has a molar mass of 28 grams per mole? That would be nitrogen.